Hello students, I'm back with another revision session. Now today I'll be taking the nuclear physics part. So first of all, you should be very well aware about how the atom structure, nucleus composition is, what is isobars, what is isotones and isotopes, and the equation one numerical is size of nucleus, which you say the nuclear size is r naught a to the power 1 by 3, and the nuclear density is independent of the mass number. Almost all the nucleuses have the same density, and that density is widely large. Then we introduce ourselves to the concept of the mass defect in the nuclear binding energy, and very important, binding energy per nucleon, which is our measure to check whether a nucleus is more stable or less likely to be stable, and its variation with A, that graph that you remember even for your board examinations. Then we have the radioactivity, what happens, how an unstable nucleus tries to attain the stability. We have three mechanisms, alpha, beta and gamma. The alpha and the gamma have the line spectrum, while the beta has a continuous spectrum. In an alpha decay, mass number decreases by 4, and remember, mass number decreases only in an alpha decay. In a beta or a gamma decay, no change in mass number. Here the atomic number decreases by 2, and if Q is the amount of energy released, we say alpha carries almost majority of the energy, that is A minus 4 upon A times Q, because the alpha emitters are generally having A greater than 210. For beta decay, we have two modes, beta minus, beta plus, and one you also call as K capture or electron capture. In beta minus, which is usually what we mean by beta decay, mass number remains the same while the atomic number increases by 1, and basically in a beta decay, neutron converts into a proton with an emission of a beta particle and antineutrino, while in a beta plus, proton converts into a neutron plus a positron plus neutrino. And you know, neutrino and antineutrino, they are antiparticles and they have very high penetrating power. In the gamma decay, nothing changes, only the quantum state of the nucleus changes, or you can say the energy level changes. Then we talk of the radioactive decay laws. So natural radioactivity follows a certain pattern. We assume if the size of the sample is large, it follows first order kinetics, and we have n as n naught e to the power minus lambda t. This would be the variation. These are the two parameters, half life and the mean life. You can also remember this equation in terms of t half and t. So you should be familiar about lambda, t half and mean life. Always remember, mean life is a bigger duration as compared to the t half, and this is the relationship between these three that you remember. Then we talk about the nuclear reactions and the nuclear fission and fusion related theory that you need to recollect, and especially in the fission you have some theoretical questions of the reactor, what is the use of a moderator or a coolant, and you should be ready with that controller and everything. Now with the questions first. A nucleus disintegrates into two parts which have their velocities in the ratio 2:1. What is the ratio of their sizes? Now in this question, we'll assume the nucleus is initially at rest, so initial momentum is 0, so final will also be 0. So the two parts will fly off like this. If it has P1, it will have P2, both will be same in magnitude, opposite in direction. So what I can write, m1 v1 would be equal to m2 v2. So what I can say, m1 by m2 is v2 by v1, which as per the equation is 1:2. And we know mass is proportional to A, that is A1 by A2, and we know R is proportional to A to the power 1 by 3, so R1 by R2 would be A1 by A2 to the power 1 by 3, and that you have this answer option D coming with that. Next one, again based on this formula, the radius of 27 aluminium is R1 and the radius of 125 Te will be, so we can directly say the ratio of R1 upon this, let's say R2 would be A1 by A2, that is 27 upon 125 to the power 1 by 3. Luckily both are perfect cubes, that comes out as 3 by 5, and you can directly say R2 is 5 by 3 times R1, so go for option A. Next one, this is a concept called the distance of closest approach that might be taught to you during electric potential or during nuclear physics or whatever. The alpha particle of energy 5 mega electronic volt is scattered through 180 degree by a fixed uranium nucleus. The distance of the closest approach will be, so what we say, it was very far away when it was coming with kinetic energy K alpha, it was very far, and this is a nucleus plus 92 E charged uranium, and this is a charge plus 2 E. It comes as it comes closer, because of repulsion, potential energy increases and kinetic energy decreases, and let's say at the distance of closest approach its kinetic energy becomes 0 for head-on collision. And if this becomes 0, we can say loss in kinetic energy is K alpha, that is gain in potential energy. Initially it was very far, so it was 0. Finally we can write it as 1 upon 4 pi epsilon naught q1 q2, that is plus 2e into plus 92e upon this r minimum. So this r minimum comes out as 1 by 4 pi epsilon naught, you write as 9 into 10 to the power 9 plus 2e, I am writing it as e because I will cancel with that ev, and let's say 92 into 1.6 into 10 to the power minus 19 upon K alpha 5 mega means 1.6 into 10 raised to power minus 13, we can say. So what we have this, or better, don't write it like this, better write it as 5 into 10 to the power 6 EV, that would be better thing. So what we can do, this E and E directly we can cancel up. So what we have, 10 to the power 9, 10 to the power minus 19, 10 to the power 6, so 25 minus 9, 10 to the power minus 14, and what you have, what you are left with, 19, 6, 25, yes, 25 and 9, that is 25 and 9, 16, sorry, 10 to the power minus 16 we have, and this is 9 into 2 into 92 into 1.6 by 5. So if I do, this is 5, I can write it as 18.4. so what we will get, this is 18, that is 36 and 9, that would be 330 into 1.6, so it would be 530, so 2 decimals will go, it would be 5.3 into 10 to the power minus 14, just checking the order, and we'll go for option C. Now based on this part, just take a screenshot of first these two questions and you can cover up. One is on distance of closest approach, one on that radius formula. Next one. Now the binding energy and the other parts. If M0 is the mass of an oxygen isotope, MP and Mn are the masses of proton and neutron, then the nuclear binding energy. What we say, the nuclear binding energy is delta M into C square, and delta M is mass of the original that parts you make use to make the nucleus. So you had 8 protons and you had 9 neutrons, minus the final nucleus, because it is stable, its mass is decreased, minus M0 into C square. So going by this, what we have, the nuclear binding energy of the isotope, from this data we can make it out would be, I think it should be the reverse of that, but you can make it out that what the question wants to say, it should be, this should be negative and that 2 would be positive. So I have available options, I'll go for 2. Ideally it should be like that, not in that way. Now nuclear binding energy we did. Now this is a plot, just see it, A, B, C, D, E, F are corresponding, the CBN is given, this is binding energy per nucleon. Consider 4 reaction, A plus B combines to C, you know that is going to be a beneficial because C is higher, it would be stable, so this will lead it to give energy, this is not going to give energy, this is not a good option. D plus E going into F, not a good option. F breaking into D plus E, yes, F breaking into D plus E will stabilize it, so 1 and 4 are going to release energy, so go for option 4. Next one. Binding energy of the atom of elements A and B are EA and EB respectively. 3 atoms of B fuse to give 1 atom of A. This fusion process is accompanied with the release of energy E, then EA and EB are. So what do you have? 3B gives A and plus energy, the energy is E. That means the final one is stable, so it has a more binding energy. Whenever we do in terms of binding energy, it would be final minus initial. In terms of rest mass energy, it would be initial minus final. So it would be EA minus 3EB we can. So what we get now as per the options, this would be, what we can say, EA would be equal to E plus 3EB, that is the most appropriate one, go for C1. Next, binding energy per nucleon of deuteron and helium is given. If 2 deuterons react to give a single nucleus helium, what would be the energy release? So what we have, 2 times 2H1 will need, and that will give us 4 helium. So if I do from the binding energy per nucleon perspective that I told you, the energy release would be final binding energy, that is 4 into 7 minus 2 into 1.1 into 2, because 2 nucleuses are given. So we can take 4 common, 7 minus 1.1, that is 4 into 5.9, that what you write, 4 9s are 36, 4 5s are 20, 23.6 MeV that you will get. So go for option 1. Next, a nuclear transformation is denoted by X N alpha to 7 3 lithium. This is shorthand notation. What we write, X plus neutron 1 0 we write, alpha we write as 4 2 helium plus 7 lithium 3. So what we know, because of charge conservation, this lower total must be same on both sides, so it would be 5, and because of the nucleon number conservation, this 7 and 4 11, so it would be 10. So 10 5 10 and 5 we can go for boron, that is would be the option here. Go for option 4. Next, a radioactive nucleus which has initial mass number A, atomic number Z, emits 3 alpha and 2 positron. 2 positrons means beta plus. So 3 alpha means mass number is going to decrease, delta A will be decreasing, and that will be decreasing by 12. So delta A decreases by 12, or you can say it loses 6 protons and 6 neutrons are lost. Now in the 2 positron emission, what happens in the positron emission? In a positron, a proton converts into a neutron. So proton count decreases by 2, neutron count will increase by 2. So total decrease in the proton count would be here decrease of 6, and here decrease of 2, so it will decrease by 8, so it would be Z minus 8, so we are left with only one option. And for neutron, 6 decrease and 2 increase, that would be 4 decrease, that would be A minus Z was the initial one, it would be A minus Z minus 4. You can do like this. Next one, 22 neon nucleus after absorbing energy decays into 2 alpha and an unknown. The unknown would be, so you can again do that. 22 neon, you write it like this. 2 alpha means 2, I can write 2 times, let's say helium 2 4, helium 4 2, so this is 2 2 4, so remaining one would be 6 means carbon, and 22 minus 10 22 minus 8, that would be 14C6, so it would be carbon. You can go for option B. Consider the following statement and state whether true or false. Nuclear fission is normally followed by emission of beta minus particles. Yes, because the products form have a greater n by z ratio as needed for that number, because we know for stability n by z ratio increases with increase in mass number. So to make that n by z ratio come to that particular level, this is a true thing. Emission of alpha is normally followed by emission of gamma radiations, and as the mass number A increases, the binding energy per nucleon in a nucleus also increases. This is not always right, so the last one is false and these two are true, so we will go for option B, TTF. That would be the answer. Now the next one, this is from the IIT 2018, and it has more than one options correct. Just see, 232 thorium converts into 212 lead. Let Na and Nb be the number of alpha and beta particles. Then how you solve this such questions? So first of all, for such questions, first of all, see change in mass number. It is changing by 20. 20 means there will be 5 alpha, because mass number changes only in alpha, and 1 that 2 by 4 in a 1, so n alpha will be 5. Because of 5 alpha, the Z should decrease by 10, but here the Z is decreasing by 8. That means there will be an increment of 2, that means the beta increases by 1, so there will be 2 beta decays. So we'll go for 5 alpha and 2 beta decays. That would be the answer here. Now you can check yourself with all these. I have these 3 questions for you. Just take a screenshot and try to solve them. Next one. Now the radioactive decay laws. A radioactive sample at any instant has its disintegration rate as 5000 disintegration per minute. After 5 minutes, the rate becomes 1250. You can make it out 5000 to 1250, that is, it becomes 1/4 in 5 minutes. That means 5 minutes is 2t half. So t half you can directly make it out as 5 by 2 minutes. But the question asks for decay constant. So decay constant you know is ln2 by t half. So ln2 by t half means this would be 2 by 5 times ln2, that is 0.4 times ln2. Go for option 2. Next one. Activity of a sample is measured at n counts per minute at t equal to 0. It becomes n naught by e at 5 minutes. That means n naught by e, that is the mean life, is 5 minutes. So the half-life would be, half-life you know is equal to tau ln2. So that is 5 into ln2. Go for option 4. Next, ln2 not log 2, just remember. The decay constant of a radioactive isotope is lambda if A1 and A2 are the activities at T1 and T2 respectively. The number of nuclei which have decayed during the time T2 minus T1. You know activity is lambda n. So A1 is lambda n1 and A2 is lambda n2. Definitely n1 would be greater, so the number decayed in that time would be n1 minus n2, that is the number which has decayed. So number which has decayed is n1 minus n2, that I can write as A1 by lambda minus A2 by lambda. So it comes out as option 2, A1 minus A2 by lambda, that you can do. Next. Two elements X and Y are found to be in the ratio 1:15 in the sample of a given rock. The age of the rock is estimated to be. Here the question language is not very appropriate. It should be Y is formed from the decay of X, and now the ratio is 1:15. So whenever X forms to Y, just remember these things. I advise students to remember, if the ratio is 1:1, it means 50% has decayed, that means the time would be T half. If it is 1:3, that means 1/4 is remaining, that means it would be 2 half. 1:7 implies 3 T half, 1:15 implies 4 T half, 1:31 implies 5 T half, and 1:63 implies 6 T half. So just remember this thing. So this is 1:15 is given, so 4 T half. So found to be in the ratio, the age of the rock is estimated to be. Actually it was a mistake when I took the screenshot, the 2 lines were missing. So the first 2 lines read half-life of an isotope is 50 years and it decays into another element Y which is stable. So here 4 T half and 50 years is the half-life, so we can go for 200 years. Next one. The half-life of a radioactive substance is 20 minutes. The approximate time interval T2 minus T1 between the time T2 when 2/3 has decayed and time T1 when 1/3 of it has decayed. Now this is a very interesting question. Just look at it on the graph. Let's say if I draw n versus t, it's something like this. Let's say it would be n naught. So time T2 is when 2/3 has decayed. 2/3 has decayed, that means 1/3 would be remaining. So it is n naught by 3 when the time is T2. And T1 when 1/3 has decayed, that means it would be 2 n naught by 3. 2/3 would be remaining, that is T1. So just look at this time window. In the start of the window we have 2 n naught by 3, at the end of the window we have n naught by 3. That means if it was x, it becomes x by 2. So always treat half-life as a time window, and in this time interval or time window the number is becoming half. So that means this gap would be equal to t half. So t half means this would be 20 minutes. So always remember this as a time window, that will help you. So it is becoming 2/3 to 1/3, that means it is becoming half of the initial one. So we can directly say its gap would be half-life. Now half-life of a radioactive substance is 30 minutes. Time taken between 40% decay and 85% decay of the same substance. Again, this is the same concept that I was talking above. 40% decay. 40% decay means the remaining would be 0.6 times n naught. And 85% decay, that means the remaining will be 0.15 n naught. So if it is x, it becomes x by 4. That means this gap would be 2t half, that is 60 minutes. Go for it. Now the next one, a solution containing 60 cobalt having activity of 0.8 microcurie, decay constant lambda is injected in an animal's body. If a centimeter cube of blood is drawn from the body after 10 hours of injection, the activity found was to be 300 decays per minute. What is the volume of blood that is flowing in the body? So first of all, it is an activity of 0.8 microcurie. Now 1 centimeter cube of blood is injected and it is having 300 decays per minute. Okay. So we are given this whole factor. So first of all, the total activity inside body would be, you can say A naught e to the power minus lambda t, that is 0.8 microcurie into e to the power minus lambda t is after 10 hours it is given as 0.84. So it is 0.8 into 0.84, and if I convert it into microcurie to our standard unit, it is 3.7 into 10 to the power 4 microfactor I have taken into effect. So this is decays per second that we have, that is becquerel you can write. Now 1 centimeter cube blood is showing a 300 decays per minute, that is 300 by 60. If I do per second, it would be 5. So what I can say, if V is the volume, so V into 5 would be equal to this much, 0.8 into 0.84 into 3.7 into 10 to the power 4. So what we are, V would be 0.8 into 0.84 into 3.7 upon 5, and if I convert it into liter, it would be 10 to the power 3 I have gone, that would be liters. This would be the answer that we will be getting. So this is 2. So this is 1.6 into 0.84 into 3.7 liters. So if I can make it out, 1.6 into 0.8 is, we can have it 130 something, 130 or we can have 1.3 into 3.7. So it basically comes out close to 5 liters. So I'll go for option 4 here. So it was a calculative one asked in JEE Main, but it could be asked because it's a very common question, so I have taken it. A mixture consists of two radioactive materials A1 A2 with half-lives 20 and 10 seconds respectively. Initially the mixture is 40 gram of A1 and 160 gram of A2. The amount of the two in the mixture will become equal after. So what we have, this is A1, this is A2. Initially you have 40 grams, you have 160 grams at t equal to 0. So let me check after 20 seconds. After 20 seconds, the A1 will become half 20 gram, it will become 1/4 because 2 t halves have passed, so it will become 40 gram. And if I check again at 40 seconds, it would be 10 gram and it will again be 10 gram. So it is, they are coming same at 40 seconds. You can directly do by this comparison. Now again check yourself. This is you can test yourself how to do this. Take the first screenshot of these two questions will be visible. Now the next two, you can see this one is a very good one. You might feel some difficulty, so you can refer to the solution on my page. And here the next three you can check like this. So take a screenshot. Let's say take off these two and this one. So try these questions, and if you find any difficulty, you can find the solutions on my page. Next, a radionucleus of mass m emits a photon of frequency nu and the nucleus recoils. The recoil energy will be, it was just something different question. So when the nucleus emits a photon, let's say photon carries a momentum p, you know that is equal to h by lambda, or lambda you can write as h nu by c, it will become. So the nucleus will also have this momentum. So if at this momentum we say P is equal to root 2 me, that should be equal to h nu by c. So E comes out as directly as h square nu square upon 2m c square. So go for option 3 here. Now the power obtained in a reactor using 235 uranium disintegration is 1000 kilowatt. The mass decay per hour will be, so mass decay per hour will be, let's say whatever be the mass into c square. So that mass into c square, 9 into 10 to the power 16 would be 1000 kilowatt, that is 10 to the power 6 joule per second. So the mass decaying per unit time would be 10 to the power minus 10 by 9 kilogram per second, or you can have it as 1.1 into 10 to the power minus 11 kg per second. That is what we are getting here. It would be minus 11. So 10 to the power minus 11 will become, if I convert it into, let's say in gram, it will become 1.1 into 10 to the power minus 8 gram per second. And if entire terms into now, but you need to find out per hour. So per hour will be into 3600, you can say hour, and this would seconds becomes 1 hour. So second will go out, and you have this this would be what you can have, it would be 360, it would be almost 400, you can say 400 into 10 to the power minus 7 gram per second. So it would be 40 microgram per second, you can go for it. So this would be the answer. Next one. A moving positron and electron, both with kinetic energy 1 MeV, annihilate with each other and emits 2 gamma photons. The rest mass energy of an electron is 0.51 MeV. The wavelength of each electron will be. So both with kinetic energy 1 and annihilate each other. The rest mass energy was also 0.51. So the total energy that would be released, that would be, you can say, would be 1 plus 1 plus 0.51 plus 0.51. So of a single gamma would be 1.5 MeV. Total energy is double. So single gamma will have this much energy. So the wavelength you can directly go. You can say that wavelength we know how to calculate. So we know this logic that E is equal to hc by lambda for it. So lambda would be hc by E, 1240 upon, we have this 1.51 into 10 to the power 6. If we do this, will be in nanometer. So what we will get now, so 1240 upon 1.51 into 10 to the power minus 6 nano. So it would be 10 to the power minus 15 meter. So if I convert it, it would be 1.24 upon 1.51, it will become 10 to the power minus 12 meters. And this is approximately 0.8, I suppose. So it would be 8.2 into 10 to the power minus 13, that is minus 3 angstrom. I think that would be the right option. Now the last one for you to test yourself, check these questions, take a screenshot of these two, and then take a screenshot of this. And this was from my side. Happy preparation.